All right, so anyway, we're in this chapter on measurement, and every science I've ever had, I've taken many, many science classes in my life, not just high school, but in college, I took a lot of them. And every science, I watched a show the other day, they were and I told you about the North Pole, and that's all they were doing is measuring. And when they measure things, they'll be able to answer some questions. And so measurement is not a frivolous thing. It's a very, very important part of science. But we do have a set of rules that are a little different than you might see in math class, don't we? Why is that? Why do we have to learn some new things about numbers because we're in science? Why don't we just use, why don't we just act like it's a math class? Anybody know what's the difference between the kind of numbers that you use in math versus the kind of numbers we have in measurements? And I know it's Monday, but what do you think? All measurements have a number, a unit, and they have error. Why does it have error? So are you telling me that we have an atomic clock that goes down to a millionth of a second? Does that clock have error? It does. What if a scientist said, but I need to do an experiment that is billionths of a second? And the clock that goes down to millionths, it has error in it, doesn't it? For you and I, a clock that went to millionths of a second, it wouldn't matter to us, would we? But it does to some people. All right. So this is the third time we've done this. Here's another set of rules that we have, and they're called, you remember significant figures? You should get those part right on the test. You should say, I can nail those. But what happens when you do calculations with significant figures? You're not going to see this in math class. If you multiply these two in math class, you better put that answer down. But number one, the calculator is so stupid, it doesn't know what a meter times a meter is. What is a meter times a meter? Right, also known as a square meter, right? They're probably measuring area. A meter to the second power is not a meter. It's a square, 1 meter long, 1 meter wide. Now, look right here. Somebody much smarter than me figured out in statistics that if you use measured numbers and you multiply or divide, you have to round to what? What do you round your answer to? This will be the third time we've had this lesson. It says right here, what does it say? When multiplying, dividing, what? What did it say? Oh, sorry. Round to what? All right, so watch now. How many sig figs are in this number here? 3. How about this one? So the least number is 3. So we'll go over here. 1, 2, 3. Now either that last 3 stays a 3 as it goes up by 1, doesn't it? Let's take a peek. Oh, you're not big enough. So it's going to stay there, right? Is that pretty easy? Let's go to the next one. Here's a division. The calculator says this number, but we have the same rule. We have 4 sig figs, 2 sig figs. I have to round to 2 sig figs. Now, is that 4 going to stay, or is it going to go up by 1? I don't know. Oh, it's going to go up, isn't it? Okay, so we put 25, and what's a meter squared divided by a meter? Okay, next, we changed the rules. Somebody, again, smarter than me, some statistician figured out, but if you're adding and subtracting, you can't use the same rule. I didn't do it. What's it say here? You have to round to what? Okay, so how many decimal places? This goes to hundreds place, tens place, ones place. What's the least number? The ones place. Now, the calculator said this, didn't it? Is that in the ones place? No. Is the 3 in the ones place? All right, is it going to stay 3 or go up by 1? Oh, it's going to stay there, isn't it? So I had to round to the ones place. I did. What do you think? That's the third time I've done that page. So if that was on the test, you'd be okay? If it says round to the correct number of sig figs? Okay, good. Very good. All right. I have one of these on the test, a ruler. This will be the third time you've seen that. How do you know how many sig, this is kind of a joke, how many sig figs do you write down when you take a measurement? How many do you write down? How many sig figs are you supposed to write down when you take a measurement? Yeah, or all of them, right? And with one instrument, all of them might be 3, right? Another instrument, that might be 4. So let's take a look. I have lines for ones place, and I have lines for tens place. So I have to do all the ones I'm certain about because of the lines, plus you have to guess one where you don't have lines, don't you? You guess one place. So if you ever use this ruler, you have to go to hundreds place. So I know you want to say 12 there because that's what a third grader would say, isn't it? The third grader just has no idea what a significant figure is. You have to tell me what? 12.00. You have to go to hundreds place. Even if you thought it was a little bit short, 11.99, you went to hundreds place, didn't you? All right, ready? Here's something new now. Let's go do. Now, if you were to, did anybody here ever shoot guns for, or bow and arrow for targets? Did anybody do target shooting? Only one, 2? Whoever takes you shooting, have you ever heard them use the word precision? How about accuracy? Have you heard them say groupings? Have you heard the word tight grouping? Okay, so what happens is, let's say that you're shooting, whether it's with a gun or a bow. Let's say you shoot like here. What would you think? Were you accurate? Were you precise? So well, I thought those words meant the same thing. And we're going to talk about what the difference between those two words are, accuracy and precision. There's something wrong here. If you're trying to aim at the bullseye and one of them goes here, one of them goes here, one goes here, there's something wrong with your technique, isn't there? So if you're a scientist and you get a number here, another way over here, another way over here, there's something wrong with the way you're doing things. But let's go down here. Look at this one. What if you were to shoot bullets or shoot a bow, arrows? What does this mean? Your shooter would say it's a tight grouping, wouldn't it? What does that mean? Is this saying accurate? Are these accurate? How do you know? What were they supposed to hit? So I had to tell you the bullseye, don't I? And that wasn't that close to the bullseye. How about them? Were they accurate? No. Were they precise? Yes. Whatever they're doing to line that gun up, whatever they're doing, and they do it the same way, they have good technique. In science, that electronic balance back there, you know why the school had to pay over $500 for it? Because it's precise. Now, hopefully, there's a little computer chip in there, and the company sends with that a mass. It's a really stainless steel mass, it won't rust, and it's 200.00 grams. It's exactly 200 grams. So when I plug it in, I can put that standard mass on there, and it better say 200.00 grams. If not, I can push a button, and I can tell the electronic balance that that's 200.00. Now, I need your attention because this is the world of science. Have you ever gone to the doctor and they want to take a blood sample or anything like that, or urine sample or anything like that? They send that to this company over in Burlington called LabCorp. They test all kinds of things there, right? And it comes back and said, I'm kind of concerned about your iron level. Your iron level is supposed to be up here at around 50 parts per million, and I really like to see it. Well, what if you send your blood to this company, and they come back and they say your blood is at 10 parts per million, and it's supposed to be at least 50. Well, then the doctor is going to ask you to probably start taking a medicine to up your iron, aren't they? But wait a minute, you stop something. How do you know that company knew what they were talking about? How did they know it was 10 parts per million? And what they do every morning, they have this really precise machine. It costs over $250,000. But every morning, they put in some fake blood that's made by chemical laboratories. 3 different laboratories said, this has 50 parts per million of iron in it. They put the fake blood in there, and the machine needs to say what on the printout? When they put it in there, say, how much iron is in that fake blood we just gave you, machine? They need to say 50. If not, they calibrate the machine, ready to go. They put another sample and it has no iron in it. What's it reading? What's it reading? I told the machine 0. I told it we're 50. And your reading came to be about 1/5, 1/5 of what it should have been. That's why the machine spit out 10 parts per million. That is a lot of science, what I just talked about. So let's take a look at this. You pay for precision. I could take a nickel, go put it on that balance, and write down the mass, come back an hour later, put it down there. I'll probably get almost identical numbers. You say probably, yeah, there might be a tiny bit off. All depends on did somebody move the balance or something like that. But they pay for precision, but then what do you want to do? If you have precision, what would you like to have? What if I eventually tell the machine where the bullseye is? Then what do you get? You get precision and accuracy, and that's what you look for. Okay? Some of you will be in the science fields. I see it. Some of you will go in the medical area. Some of you will go into sports area. Some of you will go into like maybe a PA, trainer. Some of you may do that, and you're going to have this kind of background. Now, does everybody have a calculator? Let's go back and say, I remember all your science books have these little bullseye things in there, you know? And yet, does that mean anything to you? It's like, bullseye? What? I'm in a science room. I don't see a bullseye. Where's the bullseye in the world of science? And let's take a look. Here's a student who did an experiment 4 times. Now, why would you want to do an experiment 4 times? Well, we don't know about accuracy, but we know that if I do it 4 times, if I take the average, that's probably what I should have gotten, right? Let's try that. So you put this in a calculator, and and I had another class do this already, but you go ahead and try it. Add these up and divide by 4 and see if you get that number right there. Now I rounded it off to hundredths place, didn't I? Because we were adding. So I'm gonna keep it at hundredths place. Did everybody get 73.09? Yes? All right, now let's go to student 2. See if you can put student 2 in the calculator, and something kind of unusual happens here. See what you get for student 2. Okay. Now, did you get 71.995? Well, since I can't go to thousandths place, right? Look, my weakest link is hundredths place, isn't it? So I have to round to hundredths place. That would be 72.00. All right, is that pretty easy? Okay, now, let's talk about who is more accurate. Was student 1 or student 2 more accurate? And if I just look at these 2 numbers, can you tell me who's more accurate? This is important part. Can you look at these 2 numbers and tell me who's more accurate? What do you think? No. Why not? Somebody say it. Say it.
Student 2, because they're all closer.
One more time.
Student 2, because all the numbers are closer.
Not exactly. How do I know who is more accurate? Somebody, you're leaving out the most important thing. No, that significant figures, if I had, yeah, you're right. If I had this, 3 centimeters, 3.000 centimeters, if everything was correct, I would think this is probably more accurate because it has more sig figs, right? These have the same number of sig figs anyway. But what am I leaving out? You should say, I can't tell who's more accurate because I don't know what the mean is the average, but I don't know what the what is. Look over here. How'd you know they were not accurate? I say they were accurate. What do you say? No, because they're what? Oh, you guys are way too quiet today. I think this is an accurate shot. What do you think? Why? How do you know? Close to what? That's right. What's the bullseye? I didn't even tell you, did I? What happens in science, they don't say the word bullseye. They have these words, and I wish somebody would have taught this to me in high school, because I heard this in one class. I heard a teacher say it was the known. The known. The known is the bullseye. What's another word that means the bullseye? What's another word? The standard. Okay, what's another word that means the bullseye? The accepted value. Another one. True value. And if they just told me that, it might have helped me a little bit here, right? So now, how do we figure out who is more accurate? And I'm going to show you. I didn't have room on this side of the paper, so we're going to flip this over. And what I want you to do is go down here to this bottom. And this is called the percent error equation. Now, you'll use it in this class. If you take physics next year, you use it in physics. If you take any math-based science, you're an engineer, you'll probably do a thing called percent error. Now, let me show you how to do this. It says take the experimental value minus the accepted value divided by the accepted value times 100. Now, the first time I heard that when I was your age, I'm gonna try to show you how easy this is. What do you think this means? What do you think the experimental value is? What was student one's experimental value? What was it? Yeah, right. Student one's experimental value was 73.09. Now, what was the true value? And I had to tell you, didn't I? The true value was 73.00. So let's go over here and let's put this in a calculator. So you're going to go 73.09, that's the experimental value, minus the accepted value. What was the accepted value?
73.
That was the true value, right? 73. Now, because of PEMDAS, remember your math teacher? If you didn't put parentheses around this thing on the top, you're going to get the wrong answer. So parentheses, 73.09 minus 73, close parentheses, then you always divide by what? So you think, watch here, ready? How far away was I from the bullseye? Then we'll divide by the bullseye, and then, why do I do this? What do you think times 100 means? And I'll show you. What if you got what does your math teacher tell you that 0.5 is the same as? 0.5 is the same as what? And guess what 100 does to a decimal? It changes the decimal into a percent, doesn't it? So this part of the equation simply moves the decimal over to get percent. All right, would everybody try this one now? Parentheses, 73.09 minus 73, parentheses, divided by 73 times 100, enter. Okay, tell me what you got. What did you get for student one's percent error? I can't hear you, sorry. All right, did everybody get around 0.123? Can I tell you something? That's really good. That's only a 0.1% error. That's really good. Now do student 2, just see what you get, okay? Let's try student 2, 72. So it'll be 72 minus 73 divided by 73 times 100. Now remember, don't forget about PEMDAS. Now you want to try this because even though I have the answer written down here, you need to be able to do the percent error, okay? You need to be able to push the buttons. Now the other class told me they got 1.37. Is that what you're getting? No? If you didn't, try it again, okay? If you didn't get 1.37, try it again. So parentheses, 72 minus 73, parentheses, divided by 73 times 100. Now, which student was more accurate? All right, the one with a smaller percent error, isn't that right? So student 1 wins the accuracy. Now I've chosen not to, in the 10th grade, do the mathematics for precision, but I will tell you the definition. The definition for accuracy, let's do accuracy first, right? Accuracy is how close you are to what? How close you are to what? The bullseye, what are the words they use in science for the bullseye? True value, accepted value, the known, the standard. You get that? Okay, do you know this is called a standard mass? I accept this as being 1 kilogram. This is 1 kilogram. Okay? All right. Now, what is precision, though? This is where you're not going to like this word. A lot of you think precision and accuracy is the same thing, right? Accuracy always has to do with the bullseye. What's precision? It has nothing to do with the bullseye. Nothing. This student here, they were very precise. It has nothing to do with the bullseye. So precision is how close your numbers are to themselves. How close is a set of numbers to their own average? Now take a look at this guy here, this person here. How far away, look at it, how close are you to your own average? Pretty close. Pretty close, right? I'm right on. See that? Now look at this student. How far away were they from their own average? What do you think? Who's more precise, student 1 or student 2? Okay, see this? Don't look at the bullseye. Don't look at the bullseye. How close are these numbers to themselves, their own average, right? Pretty close, aren't they? What about these? Not as close or not? So who's more precise? Student number 2. Let me give you an easy example. Ready? Here's student 1. He does the experiment once, gets 1 gram, 2 grams, 3 grams. All right? What is his own average? What's the average? Everybody know, what's the average for any 3 numbers in a row? What's the average of 59, 60, 61? Do you know it's the middle number? What? Ready? What if I do odd numbers? What's the average of 1, 3, and 5? What? What's the average of 5, 10, 15? What? It's 10, isn't it? Anyway, so what's this person's average? 2. Now, look, how far away are you? I'm on, but I'm, okay. What about another student does this? What if a student does this? They get 1.1, 1, 1.1. Which student was more precise? Anybody know? Let me put a 2 here. That'll make it easier. The average is 1.1, right? Which student has a more precise set of data? Number 2, right? Because look, how far away are you from your own average? Like 0.1. Which one's more accurate? Student 1 or 2? And this will tell me if you're really listening today.
We don't know.
Excellent. Why don't I know?
Because you don't know the true value.
I never told you the bullseye, did I? So I can tell you this is more precise because they're close to each other, aren't they? And these are further away from each other. But I can't tell you the accuracy because I don't have the bullseye. Yes? Yeah. What do you think? All right, I'm ready to leave that. Now, 2 more vocabulary words, and then we are on our way to the last thing. If you were to pick up almost any book that was on math-based science book, like physics, chemistry, even sometimes geology, okay, they have these 2 Q words, okay? Quantitative and qualitative. Now I'm going to give you an example. Some of you, when we did the candle lab, you did a qualitative observation. The candle was white. It had a certain amount of smoothness to it, right? And you were using words to describe it. That's called the qualitative. But some of you actually measured the mass of the candle and measured it again and measured it again. Or some of you put beakers over the top and said it took this many seconds before it went out, this many. And whenever you do an observation that has a number in it, it's called a what? Quantitative data. The word quantity in there, it always has a number, doesn't it? If I look at a salad and it said, there's a tomato, there's a cucumber, there's a lettuce, and there's a carrot, what kind of analysis am I, what's that, what kind of analysis of my salad is that? Qualitative. But what if I take all the tomatoes out and I weigh them? And I take all the carrots out and I weigh them and I give you a list by mass. Then what is it called? Everybody get that? I hope this never ever happens to you, but if you're riding in a car with somebody and you get pulled over by the police and your friend, quote, friend, happens to have a bag in their car of white powder. The policeman, who probably did not go to college in chemistry, will go to the back of their car and get a little kit out. And they'll poke a little hole in that bag, and they'll take a little bit of that white powder, and they'll put a drop of this indicator thing on there. And if that indicator chemical turns purple, you're going to jail. Now, what does the police officer know? The only thing they know is cocaine. That's all they know. But you're going to jail. You get it? Everybody in that car is going to jail. Now, what are they going to do with that cocaine later? They're going to send it to either Raleigh or Charlotte, and they have some very sophisticated scientists that work for the police department. Some of you could do that for a living. I want to be a scientist who works for the police department. And they're going to use a thing called a mass spectrometer. Very expensive piece of equipment. And they're going to analyze that, and they're going to have all kinds of numbers on and what percent of it is this, what percent of the cocaine is this, and if whoever made that cocaine, if the glassware had an impurity to it, some kind of dirt to it, it's going to show up on a mass spectrometer. And they'll say, you know what? This cocaine matches the cocaine we found that was sold over there in Burlington. Maybe the same person's making it. And all those numbers would be a quantitative analysis, wouldn't it? You ought to be a little afraid if you're a criminal, because if you were to break into a building, let's say a bank building downtown, and you thought you got away with it, and the police came to your house and you said, "Well, they won't catch me. I threw away all my clothes and everything." But then in your shoes, because you broke some glass while you were there, you said, "Well, I cleaned those off." Now they'll find little pieces of glass still embedded, and they'll put it in a mass spectrometer. And they'll say, you know that glass in that building? It was the only building that has that kind of glass was that one. And you were there. So they would do a quantitative analysis of that glass, wouldn't they? All right, so what do you think? Here's our last thing we're going to do now. This is the very last thing that we need to do, and we will be done. I want you to go to this page right here. And what I want you to be able to do, there was one part of the homework where it asked you, I didn't want you to be exact, I wanted you to be to estimate. It's too bad. Some of you, I say, well, I don't even want to learn the metric system. Well, that's too bad. You have to. And the rest of the world, they don't really have to learn your system. Some of them do anyway. I ask, we have a Chinese exchange student here in another class, and they do teach them English. Why? Because they think that that's going to help them to succeed. They also have learned a lot of the English things. They don't have to. But you can't sit down and say, I don't want to know anything about metrics. You could at least be able to estimate metric things, couldn't you? So that's what we're going to do here. All I want you to be able to do in this last part of the lesson is estimate things. So here we go. Why is there a picture of a paper clip on this handout sheet? What should you know about, not a jumbo paper clip, just a regular little paper clip? Why is it on there? Tell me something about the metric system that has to do with paper clip. How much is it? 1 gram, okay? There's no way that you can tell me you don't know what a gram is. You get it? What's a gram? Oh yeah, paper clip. Okay, now, I didn't have a picture of a nickel, but it's a coincidence. It's a coincidence, but a nickel has a mass of how much? 5 grams. There's no way you don't know what 5 grams is. You get it? You got it? How much do a quarter weigh, you think?
25.
And that's that math part. See, I love the fact that you guys like math, but no, it's about 5.3 grams. But I know what you were thinking. You were thinking mathematically, weren't you? But it's just a coincidence that the nickel happens to be really close to almost exactly 5 grams, okay? Let's do, does anybody happen to know how much this is?
100 grams.
What's a kilogram? Anybody know about this one? What's a kilogram? About how much do you think this is? And
100 grams.
2.2 pounds. What's 1,000 grams? Kilo means 1,000. So it's 1,000 grams. So it's about 2.2 pounds, isn't it? My son was he has lived in Thailand for the last 13 years, but I talk to him all the time, and he is they had a complete lockdown over there, COVID. He actually they couldn't even go to the parks. He couldn't exercise, and anyway, he's just been kind of doing all this stuff remote, his work remotely, and he said he had been gaining some weight, and he said, I've never been, only once, that's the first time in my life I actually reached 100 kilos. And so that means he was at 220 pounds. Now since then he's cut back and he's down to 90 kilos, which is 90 times 2.2. But he wants to go down even further than that. All I'm asking you to do is don't act like you're dumb. The rest of the world knows what a gram is. The rest of the world knows what a kilogram is. You get that? All right, let's go on. Why is there a picture of a door and a doorknob? What's that supposed to be? Look over there.
The height.
The height from the floor to the doorknob is usually about what?
A meter.
Very close to a meter. So how tall is the ceiling in meters? You say, wait, I didn't think I could do this. I can estimate metric things? How much? Less than 3, but between 2 and 3, right? Between 2 and 3 meters. I can do that. Which one's longer, a meter stick or a yardstick?
Same thing.
Oh, they're close. They're close, but which one's longer? You look up here.
The meters.
A yardstick is what? 36, and it's about 3 1/3, a little bit more than 3 inches longer than a yardstick. So if you know what a yardstick is, and watch, there's a meter stick, right? If this is a yardstick, there's a meter stick. But they're similar. How long do you think a football field is in meters? If it's 100 yards long, a meter's a little bit bigger than a yard, so it's going to be less meters, but not a lot less. What do you think? 100 yards, how many meters do you think? 90 something, probably. In the 90s? Okay, I can do that. All right, what about, now they use a fingernail. I don't use a fingernail. What I do, my ruler. All right, at some time in your life, you should pick up a metric ruler and use your little finger, use the edge of your little finger. My fingers are a lot bigger than yours, so I know that my centimeter is right here. I have a centimeter right there. Some of you, your centimeters are way down here. You got that? But every one of you should be able to know what a centimeter is, don't you? There's no way you should be able to not be able to estimate centimeters. And don't ever, in my class, don't ever pick up one of these rulers and say, which one is centimeters? I'm going to say, let me see your little finger. Nobody in here has a little finger that's that wide. Nobody. That can't be centimeters, can it? All right. Next, why is there a dime on here? Why are they showing the thickness of a dime? Aiden, what do you think? Got to be some reason they put it on there. Uh-oh. What's it say? That's what it is. So I think sometimes about a millimeter, isn't it? Hey, I know what a millimeter is. Which one's longer, mile or kilometer? I mean, if you don't know which one's longer, that is sad. It's sad. Which one's longer, mile or kilometer? A mile. Now, how big is a kilometer compared to a mile? Watch now. If I were to draw a mile, I go to half of a mile and go a little bit further. Go to 6/10 of a mile. There you go. And 0.6 miles is a kilometer. Get that? It's a little over half a mile. Yes? So if you can estimate half a mile, go a little further, and that's called a kilometer. All right. I got one more minute here, okay? Let's see. Oh, it just so happens that if I did ask this question, it'd be a bonus question, but do you know in your car, it has 2 speedometers on it? And if you're going 60 miles per hour, and everybody can remember that number 60, that's 100 kilometers per hour. Now, you know what fraction you can make out of that? 3/5 and 5/3. So let's pretend that you're going to go to Italy as a senior, and you're going to be in a bus ride, and they say it's 100 kilometers away. 100 kilometers away. There are always more kilometers than miles because they're smaller, right? What would I multiply that by to get how many miles? 3/5 or 5/3? I gotta make it smaller for miles. What is it? 3/5. What's 3/5 times 100? 60. Okay, isn't that right? All right, that's enough for a day. Can you make a promise to yourself? I know you're tired, but if you have not started your homework, it's an easy grade. You've got to say, I've got to get at least 20 to 30 questions right today, and then I'll be done. All right, thank you very much.